Hello everybody, welcome to our video solution to problem 1 from Quiz 11, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this first problem from the quiz, we have two vector spaces V and W, and we can see immediately that they have the same dimension because, look, they have bases of the same length. So V1 through Vn is a basis for V, and W1 through Wn is a basis for W. Our goal is to define an explicit isomorphism from V to W. So, first thing, what does it mean to be an isomorphism? All right, well, this should be some linear map from V to W. So this is a linear map from V to W, and it has to be a bijection. Now, the good news is, when you're trying to prove that a linear map is a bijection, and you know that the codomain and the domain have the same dimension, then you actually only need to show that it's an injection or a surjection. All right, so it'll be enough to show either an injection or a surjection. And it turns out in this case, we're going to be showing that we have a surjection, right? And you'll see why in a second. So, the key here is I want to define an explicit isomorphism. Means I need to tell you exactly what the map does. Now, defining a linear map is a lot easier when you know a basis for the domain because you can simply use the universal property of a basis. So, by the universal property of a basis, there exists a unique linear map. Okay, this is beautiful, right? We don't have to prove linearity, right? We just know it's going to exist. A unique linear map, let's call it T, from V to W, such that, okay, all I have to do is tell you what T does to a basis. Okay, well, the basis is V1 through Vn, so I'm going to tell you what it does to, say, the ith basis vector. And the most obvious thing to do is just send it to the ith basis vector of W, namely Wi. All right, so this is for all I. All right, so universal property of a basis just stops right there. Like, you tell it what it does to a basis, you know there is a linear map, and it's unique. Boom, we win. Now, I need to show that this unique linear map from V to W is actually a bijection. All right, now, one of the places where students get into trouble here is they say, oh, look, I have a linear map, the dimension of V and W is the same, therefore it's an isomorphism. And that's not good enough. There's a lot of linear maps from V to W that are not isomorphisms, even though V and W have the same dimension, even though V and W are isomorphic. All right? So we need to actually show that we have injectivity or surjectivity. And in this case, I'm going to show surjectivity because of just how nicely we've set up the definition of T. Now, surjectivity means that every element of the codomain, okay, so the codomain is W, all right, so surjectivity means that every element of W has a preimage. Every element of W has a T preimage. Okay, well, what does an element of W look like? All right, so if W is an element of W, then, well, we can use Einstein notation, and we know that we have a basis. So there exist, say, A1 through AN in F, right? We're assuming V and W vector spaces over some field F, such that W is equal to AI Wi. Okay, so again, I'm using Einstein notation here. This says W is this linear combination of the basis vectors. Okay, so can I see W as being in the image of T? That is, does it have a preimage? Well, it's actually pretty easy to see. If I apply T to the element given by taking the same linear combination, only using the V's instead of the W's, this is equal to, well, T is a linear map, so I can pull out the A's. And we know what T of Vi is. It's simply the Wi. So this is AI Wi, which is equal to W. And there we go. We're done. We've shown that this W, this arbitrary element of the codomain, has a preimage. And there we go. Okay, now, just because I know some people don't like to use the surjective part, right? It's just, it just looks too easy or something. Let me show you how you would have done the injectivity portion. Okay. Now, for the injectivity portion, right, so this will be an alternative proof for the injectivity. So injectivity, well, again, for a linear map, all we need to do is show that the null space is 0. All right, so to show injectivity, all right, it's enough to show that the null space of T is equal to 0. All right, well, let's let something be in the null space. So we'll let V be in V such that TV equals 0. Okay, well, again, we can write V in terms of the basis. So there exist, let's call them something a little different this time, maybe B1 through Bn in F, such that V is equal to Bi Vi, again, using Einstein notation. Okay, so now what do we have? Well, we know that 0 is equal to TV, but V we can replace by Bi Vi. And now we can pull the Bi's out of the linear map. And we know exactly what the T does, right? Again, we have TVI equals Wi. So this is Bi Wi. And so I've now written 0 as a linear combination of the Wi's. But we know that the Wi's are linearly independent. So since W1 through Wn is linearly independent, well, if you have a linear combination of a linearly independent list and it's equal to 0, then the coefficients have to be 0. So we have B1 through Bn equals 0. But what does that mean? Our original V is just equal to 0 Vi, right? I'll put a little I down here so we can sum over it. So V is equal to 0. And this shows that the null space, right? Remember, we took an arbitrary element of the null space when, we wrote let V be in V, such that TV equals 0, right? So this means V is in the null of T. So we took an arbitrary element of the null space and we showed it equals 0. So the null space is equal to 0. Okay, so that would be another way of doing this. But I think actually the surjectivity proof is much simpler here. All right, we will see everybody next time.